Regarding solution of the question, the velocity v and displacement x of a particle executing simple harmonic motion are related as v dv by dx equal to minus omega square x at x equal to 0. V is v naught. Find v when displacement is x. Find v when displacement is x. Here you first separate the variables. V on one side, x on the other side. Put the integral signs on both sides. When x is 0, v is v naught. When x is x, v is v. We want v when x is x. Now left side is x to the power n pattern, x to the power n plus 1 by 2. From v naught to v, omega is a constant, minus is a constant, integral of x, x square by 2, from 0 to x. In place of v putting v, in place of v putting v naught, in place of x putting x, in place of x putting 0. So v square minus v naught square by 2 equal to minus omega square x square by 2. That means v square equal to v naught square minus omega square x square, or v is under root of this whole thing. Now just let me know if you have any question regarding this. If you have a doubt in a specific step, take the pointer there. Significant figures. Now we will be talking more of physics and less of mathematics. If you are given some instrument to measure something, let's say scale, the ordinary scale. Supposing, or in fact I can make some instrument just for discussion. Suppose you have this instrument and you are trying to measure some length. This instrument has markings as 0, 1, 2, 3, 4, and that's it. What you are trying to measure is let's say this. Now you are dead sure that this thing has a length more than 1 and less than 2. But between 1 and 2, you're not sure. So you make a guess. You think it is somewhere in the middle, so it's 1.5, whatever unit. Your reading is 1.5. But according to the instrument, you are sure about 1. You are not sure about 5. 5 is called the doubtful digit, and we often use it in experimental measurements. Human judgment. And these two jointly are called significant figures. These two are jointly called significant figures. So 1.5, how many significant figures are there? 2. So significant figures contains doubtful digit in it. Now, why we are discussing this thing? In calculations, if you have calculators, for example, then it will give you answer up to so many decimal digits. 5, 7, 8, 9, 10. But if you are doing calculations based on experimental readings, if I am not even sure about this number, then how do I say that when this number is multiplied to maybe pi, then the answer is 4.71238898. If I'm not even sure about this number, on what basis can I give answer up to so many decimal places? That's the basic idea of this discussion, significant figures. In science, when you perform experiments, then there are limitations of your readings. They are limited by the instruments that you use. And when you do calculations based on your readings, and cancellation is not taking place properly, then what's the point in giving decimals 4, 5, 6 places if your readings themselves are not so accurate? So that's the basic idea, and this concept would work in physics also and in chemistry also. So some rules have been made keeping this point in mind, that you can't give too accurate answers because your numbers themselves were not so accurate. Some rules have been made for addition, for multiplication, division, subtraction. And these rules are to be followed in science calculations normally. When we talk about something as pi, we don't have any doubt in our minds about the digits in pi. For example, if I say pi is 3.14, it is not that what comes beyond 4 is not known. It's so easy to tell what is beyond 4. But what's the use if your other things are not accurate? But regarding pi, you have the answer up to several decimal places. When you know some number for sure, then it's called a sure number. There is no doubtful digit associated with a sure number. So when we say sure number, like I say that make 3 measurements and then we will take the average. And you do 3 measurements and then we take the average of the 3. So obviously you will divide by 3. 3 readings you will take and then you will divide by 3. In your lab also you do these types of things. If you have to measure diameter of some object, you will use your instrument at 3 places or 5 places, note down 3 or 5 recordings and then take the average. This is done to reduce the error margin. Now when you are dividing by 3, what is the doubt about number 3? There is no doubt about number 3. You have taken 3 readings, so you will be dividing by 3. There is no doubt associated with 3. There is no doubt associated with pi. If we want, we can give the answer up to millions of decimals, millions numbers after decimal, if we want that way. So as far as 3 is concerned here, there's no doubt about it. So this is called a sure digit. So when you do such type of calculation, your reasoning should not be like this, that I'm not even sure what comes after decimal. I'm not even sure what comes after decimal, so how can I give such an accurate answer? You are sure what comes after decimal. If you are dividing by 3, you are sure what comes after decimal. 3 readings you have taken. So you know what comes after decimal. It is 0 which comes after decimal. If you have taken 3 readings, you know after that also what comes? 0. After that also you know what comes. So this type of 3 is different from this type of, let me make it 3. That type of 3 is different from this type of 3. Here is it 3? Well, slightly to the right, maybe. This 3 and that 3, they are completely different from each other. Where here, there may be some judgment, doubtful digit. Somebody can say 3 point, maybe 1. But here, where is the doubt? You have taken 3 readings, you will divide by 3. So, when you have sure digit, then you know everything about it after decimal. 3.0000000000000. It will never end. Right? So that's about sure digit. But regarding experimentally measured value, you will have limitations. The ordinary scale that you use for measuring the length, that scale can't go closer than a millimeter. That scale can't go closer than a millimeter. Now, if you want to know thickness of hairs, you can't use it. Every instrument has got least count. It cannot count lower than that. That's the least it can count. So the commonly available scale that you use that cannot count below 1 millimeter. So every instrument has got some lowest limitation. 1 millimeter is better than 1 centimeter. Imagine if your scale had such type of thing, that would be a bad scale, isn't it? Such distant markings 1 centimeter apart, then your reading will be crude. Likewise, if you have a meter stick with no markings in it, just imagine how bad that instrument would be. You can't measure centimeter using that. If you have a scale which does not have millimeter markings, only centimeter markings, you can't measure millimeter using that. So every measuring instrument has got limitations. So we talk about least count of a measuring instrument. So if you will find there are instruments which can go better than the ordinary scale, vernier calipers, screw gauge, they can go better than this. Now, without knowing about the instrument used, there can be problem. Without knowing about the instrument used, there can be problem. For example, somebody suppose tells me that I measured something and it is around 50 centimeters. It is 50 centimeters. Now, 55 and 0. Should I take two significant figures in this number? That same answer of 50 centimeters, when converted to millimeter, is 500 millimeters. So should I take three significant figures now, 5, 0 and 0? Same answer can be given in meter also. Half meter, 0.5 meters. Well, even if you look at these two, I hope you get the point what I am trying to say. 50 centimeter information does not tell me that I should consider two significant figures or three significant figures. Imagine centimeter is converted to angstrom. How many zeros you will have? 0, 0, 0, 0, 0. It will go on and on and on. Will you consider all those zeros for significant figures? So, unless the person who has done the measurement tells you something about the instrument he used, it may be difficult to conclude how many significant figures are there. To overcome this problem, certain practice is followed. And that practice is, we just won't consider zeros as part of significant figures. We won't consider zeros as part of significant figures. What would we do? 5 into 10 to the power 1. Write them as 10 to the power. 5 into 10 to the power 2. Whatever you want to say, just write in 10 to the power for zeros. Now, if you want to say that I use the superior instrument, then you must tell it from this 5. You want to say that I had a superior instrument, make it look like this. 5.0 into 10 to the power whatever you want. 5.00 into 10 to the power whatever. 5.000. 5.000 is a much deeper measurement. It means you are trying to tell that my instrument was so powerful, so capable, that I could measure up to the 3rd place of decimal. So whenever you see zeros like that, 500, 5,000, 5 million, just ignore all zeros. Write whatever number you have in this format. And look here. Is it 5? Is it 5.0? Is it 5.00? Is it 5.000? If you have a superior instrument, it will be able to tell you up to more decimal places. The superior is the instrument, superior in the context of decimal places. Superiority of an instrument can be in different respects. I'm talking in the context of giving deeper answers. That is, if a meter stick and millimeter scale I'm calling better right now. It can give me a deeper result. Meter scale can only tell me 1 meter, 2 meter, 3 meter. Of course, I can use some doubtful digit. I can say 3.5 meters. That 0.5 is coming from my judgment, or is called a doubtful digit. 5 will be a doubtful digit. But if I have multiples of meter, then my answer will always be something like this: 3.3 meter, 2.5 meter, 2.4 meter, where I am judging this for. If I have a meter scale, if I have a millimeter scale, I can give a better answer. So, if you want to say that you have a superior instrument, show it like this. Then it can be told that significant figures are 4 or 3, but not by looking at this. I hope you got this idea, and if you have any questions, then just let me know. So we are going to discuss several rules. So one rule we discussed just now, that if you find several zeros, just ignore. Just ignore. Right? But if you see something like this, then it means there are 3 significant digits. When I say 3 significant, last one will be doubtful, always. Significant digits include doubtful digits. So that was one rule. Then again, that zero problem can come after decimal. Zero problem can come after decimal. So if I want to say 1 centimeter, it can be 0.01 meter. Now 1 centimeter, 1 significant digit, 0.1 meter, 2 significant digits. Doesn't make sense. So again, if you find zeros like that, just ignore. Just ignore. I'm not saying ignore it when there is 1 here. Just 0, 0, 0. This is 0 and these are all zeros. Then ignore them, all of them. So if you have something like 1.003, how many significant figures does it have? 1, 2, 3, 4. If you have something like this, how many significant figures does it have? 1. If you have something like this, how many significant figures? 1. If you have something like this, how many significant figures? 1, 2, 3. But if you have 301, then you have 1, 2, 3. 3 significant figures. Now comes the question of multiplication, division, addition, subtraction. The general philosophy is always this. If you have made several readings using different instruments and done calculation based on them, never try to give more accurate answer than your worst reading. Never try to give too accurate answers, because the readings themselves would decide. If you divide, for example, two numbers, supposing you have one reading as maybe 13, and other reading as 5. These are readings, measurements. You're not taking average of 5 numbers. You have measured 5 by some instrument. Now when you divide these, see what you get using just division. No concept of significant figures, just division. See what you get. 2.6. Okay, but then 5 is having only one significant digit. The rule for division is that you can't give answer better than your worst reading. You can't give your answer better than your worst reading. 5 is the reading, not average. 6, no. So what does one do in such a case? In such a case, one has to do rounding off. We are not just going to forget 6, but we are going to do rounding off for taking its weight into account. Rounding off rules are also there, where we take the weight of this into account. So what are the rounding off rules? You want to have only one significant figure in this case. That means you want to round off here, right here. If the number next is 6, here like this, then your answer would be 3. So 13 by 5 is 3. So after this, if you have more than 5, then you will increment it by 1 unit. That's how 2 became 3. 13 by 5 equal to 3 looks quite may not be okay, it may not look okay, but when you understand that you are dealing with readings which themselves have limitations, then you understand it better. Otherwise, you are always tempted to say 2.6. Now, if you want to round off here, and if something after that, the next thing after is more than 5, then this will increment by 1 unit. What if it is less than 5? Well, it won't. What if it is 5? If it is 5, then if this is even, it won't increment. If it is odd, it will increment. I repeat, more than 5, increment. Less than 5, no increment. Equal to 5. If it is even, don't touch, leave it as 2. If it is odd, increment it. That means we are preferring to write even numbers. So for example, if you are to round off 2.5, right here at this place, then because 2 is even and this is just 5, you would write 2. Okay, so that's the division rule and that's the multiplication rule also. Don't give your answer which is more accurate than your worst reading. So you need to round off accordingly. Let me give you some rounding off practice. Just give 3 significant digits, only 3. That means you have to round off this place. Oh, this is more than 15,000. This is more than 15,000. I was ignoring this because it was after decimal. But you can't ignore these. They will become zeros. They will become zeros. So, yes. 155,000. That is 3 significant figures. We discussed that rule, right? Zeros at the end don't contribute to significant digits. It is as good as 155 into 10 to the power 2. So 3 significant figures are there here. Now try this one, 14.745. Again, 3 significant figures. After 7 it is 4, less than 5, so it will be 7 only. It will be 7 only. 14.7. That would be the correct answer. Any questions regarding these 2 cases, just let me know, or let me put up the third one. Third one is 14.750. Rounding off up to third. 3 significant figures we want. .8 because after 7 it is 5, so 7 is even or odd. 7 is odd. 14.8 should be correct. Any questions about this case? Let me know. Now try this one. 14.650 into 10 to the power 12. Again, 3 significant figures. It's a big number, very big number. Yes, 6 is even. So 14.6 into 10 to the power 12. That would be correct. So this was some rounding off practice. Now we can do some real multiplication and division calculation. consider that whatever is given to you is based on actual experimental measurement. Calculate this. Yes. Well, you can see that your worst measurements are 2, and these measurements have 3 and 3 significant figures. Your answer cannot have 5, 3, 4, 6, 2, 4. That has 5 significant figures. Also, I think you need to check your calculation also. The answer that I have is somewhere near 1000. That's close, but you need to check. Just tell me one thing, without significant figures concept, what are you getting? Just the calculation part. Okay, you could be still doing it. Let me check. I'm getting 1039 years, 0.78. Yes, but 8 will not be required actually. 3 significant figures we need. And for rounding off, if you want to round off up to 3 significant figures, then 4 digits are enough for calculation. That means I don't need both of them. So saving some calculation time, just saying after decimal there are some things. Now you have to round off here. After 3 it is 9, so 3 will become 4, yes, that's correct. 1040. Now, if you have any questions regarding this, then just let me know. Before we go to addition and subtraction, some more practice I will try to give you. 1001. Tell me how many significant figures are there in 1001? That's very good. And how about 100.1? Same, yes. How about 100.10? Five. Yes. 5 is correct. So had it been 100, 10, Had it been 100, 10, situation would have been different. Answer would have been 4. But it is 100.10. So answer is 5. If you have any question anywhere, just ask. Now next one is this 0.001001. Okay, there is a private message about this one, and the answer is here. Answer is here. How many significant digits are there in 60000? Answer is 1. Because it is written as 6 into 10 to the power 4. Significant digit is only 6. Regarding this, yes, zeros are ignored. If this is 0 and these are also zeros, yes, so 4 should be correct for this. 4 should be correct. More rounding off practice. 3472. Up to only 2 significant figures. No, 3500. 3500. Yes. 84.16. Two significant figures. 84, yes. This should be 84. 2.55. 2 significant figures. 2.6, yes. And 28.5. 2 significant figures. 28, yes. Any questions regarding this? Just let me know, or we go to the next one. Now regarding the pi, what do you do regarding pi? You see, volume would be pi r square h, and radius as 3, length as 3 and radius as 3. So for pi, you can take 3 or 4 significant figures. That's it. Not more than that, not required. So if you take 4 significant figures four after decimal 3, after decimal 3, .142, that you can take for pi. Just calculate and round off up to 3 significant figures. Just calculation. It's coming out to be how much? Just the calculation without significant figure rounding off, 43.68. Now since we have to round off up to 3, one more number will be required, because that number decides the rule for rounding off. This number is 8, that means this will become 7. 43.7 centimeter cube. If you have any questions, then just let me know. Just a moment. I think first we discuss the addition. First we discuss addition rule. Now the basic idea I have told you behind these calculations. For addition, this is the method which is followed. If I explain it with illustration, I think that will be clearer. Suppose you want to add 24.36, 0.0623, 256.2. Then, how would you do that? The rule is that write them like this. 24.36, one below the other. 0.0623, then 256.2. how to write these so that decimals are in one vertical line. Decimals are in one vertical line. Start watching from the left for the first doubtful digit. Start watching from the left for the first doubtful digit. In every measurement, the last digit is the doubtful digit. Start watching from the left the first doubtful digit. 6 is far away, 3 is very far away, 2. This is the one nearest. Round everybody, right there. So I am rewriting what will come after rounding. Okay, everybody has been rounded off now, and now just add. Just add now. Let me recheck or 2. $20.7. Like multiplication and division rules are similar, addition and subtraction rules are similar. Any questions about this procedure? Let me know. Let me check. $2.17 is the answer that I have. Millimeters. Now here when you divide by 3, 3 is the sure number, right? 3 is a sure number. If anybody would like this to be discussed on the board, then raise your hand. You can start this now. Let me check. Well, yes, that's correct. 39,000. If anybody would like this to be discussed on the board, then raise your hand. We stop at this point.